And the next thing we look at is the turbine. These steam turbines are used largely for power generation, and also in the case of ships and submarines for propulsion. We look at a nuclear submarine or a nuclear aircraft carrier. It has a nuclear reactor which produces steam. That steam runs a steam turbine, which produces some electricity. But gas turbines also use stationary applications like power generations. Gas turbines are also used for propelling naval ships. Not so say cars. Traditionally, we do not look at in a this course. The working substance is water and different from steam. We met this is water that's there in a river or in a dam. This gives you the idea of a hydro turbine. And the equation you use there, although they came from fluid mechanics, the basic idea was that it did satisfy the laws of thermodynamics. We call hydro turbines, and they are used for producing electric power, and in some cases running mills and turbines. So the working substance, if it is steam, we have to take it as from the property tables data. Here we assume it to be an ideal gas. Hydro, we assume it to be a compressed liquid. And here we have to worry about what I mentioned in the case of pumps. You have to take care of cavitation. So that's one thing to worry about. Okay, so give some idea of what are the sizes of machines. The biggest turbines that are there are steam turbines, which have gone in power up to 1,300 megawatts. And then all the power generation devices. And there are smaller machines. A propulsion turbine could be like 3 megawatts to 5 megawatts. Gas turbines, the biggest stationary gas turbines are of the order of 130, 140, 160 megawatts. Aviation turbines, we don't talk of power, but we look at what sort of a thrust we can make. Tank converters, these are about 1 to 2 megawatts. We'll draw that on. So what are the assumptions we have seen there? What equations we have that we have looked at? We assume that if there is no other information given about this thing, we say that this is adiabatic. If it is specifically mentioned that it loses some heat, some Q dot Cv is there, then we take that value in the first law equation. Otherwise, if there is no mention, we can assume that the turbine is adiabatic. Now we see what it looks like on the property diagram. It's a TS diagram. And if you are looking at steam turbines, we have to show the dome. And in this case, as I mentioned, what you would like to do is avoid a two-phase mixture inside of machine like a turbine. So in power stations, we start off with superheated steam, say there, expand it up to this point in one turbine, and then we take the steam out, send it back to the boiler for heating it again, and then bring it back almost at the constant pressure to the same temperature, and then we start expanding it in not just one turbine but multiple turbines until it gets the temperature that is there for us, 45 degrees Celsius or so, slightly wet steam in the end of the turbine. That's where we have to be careful about the engineering of it. So that's what power steam turbines would do. Nuclear turbines would have pressure somewhere, say over there. They produce dry saturated vapor from a nuclear reactor, and this is expanded. And as you keep expanding, the quality keeps going down, so that engineering keeps getting complicated. So we say that, okay, I will come to a point where X is of the order of say 0.8 or 0.85, and then I cannot tolerate too much of liquid in the turbine. it will break my turbine. So what we'll do is we'll take this steam out and physically separate the liquid from the vapor because there's a big density difference. So the vapor state, when it is separated from here, will come over here. The liquid state from here will come over there, and then we put it into another turbine and expand it until the cooling temperature is there. So this is a physical separation device. We will look at this later on in case when you look at another type of an application. But that's what happens in nuclear turbines, and including nuclear turbines on ships and submarines. We are always dealing with a wet substance, and you have to always be very wary about it. Okay, so that is it. And then what about gas turbines? So gas turbines, we do not show the dome. We assume that we are far away from this dome, way at the top, somewhere over there, much beyond this. So when we make a gas turbine diagram, we'll put this as T and S. We won't show the dome at all, and we say that the gas turbine expansion is from, say, there to there in the ideal case, and in all cases, if it is an isentropic turbine, the specific entropy will increase, but the discharge pressure remains the same, just like this. In this case, the constant pressure lines are like that. So this is P1, P2, and the anisentropic turbine, in this case, it will start from here, but it will end up over there. This is 2S, this is 2, this is 1, this is 2S, this is 2, and in this case, the throttling, if it is an isentropic turbine, the quality will slightly improve. So here is one practical advantage we get of throttling, or say friction, or irreversibility, but it works to our advantage as far as an engineer is concerned. Thermodynamically, it goes against us. Okay, so these are the type of turbines that are there. If it's a hydro turbine, well, on the same diagram, it will be completely on this side, but it will be too small. So if we blow it up and we say that, forget about that, we are only looking at compressed liquid, S and T, then the hydro turbine will be like this. Okay, so that's how we show the processes for the steam turbine, all types of turbines. These happen to be exceptionally sophisticated machines. They are rotating with very fine clearances, and these temperatures, as I mentioned, we are continuously trying to increase this temperature to get better and better thermal efficiency. So that's about the turbine. Now let's take a few questions that are there, and then we'll continue.
Morning, sir. My name is Sarabjit Singh, and I want to ask a question that's what is the difference between classical and statistical thermodynamics?
Okay, so we'll take that up. Okay, so the question is, what is the difference between classical thermodynamics and statistical thermodynamics? We start from two very basic, different concepts here, but at some point, under some assumptions, statistical thermodynamics becomes classical. In statistical thermodynamics, we look at every atom or every molecule and assign some properties to it, irrespective of the phase. Most notably, if it is in the gas phase, then we apply the kinetic theory of gases. We assign some properties to every molecule, and then we look at the statistical average, because there are too many of these molecules, we cannot talk about each and every one of them. So we look at the statistical average and start developing theory from that point. So we look at all molecules, take a very large ensemble, and say, now what does the average look like? And from there, what do I get in terms of pressure, in terms of energy, in terms of various other things that we know. In classical thermodynamics, we say, well, we are not going to look at each and every molecule. We can say we will make the assumption that we are looking at a continuum, which means that the smallest element of the substance that we consider, and this one can approximate this, say, as the cube, has got enough molecules or atoms in it that the statistical average of this is good enough to tell what the entire element is all about. So whether it is pressure, temperature, enthalpy, all of that we can get by looking at sort of an average of all of these, and we will not worry about where that average came from, but we start off by saying that this is the smallest element we have, some size we can put on it, This is of the order of angstroms, a fraction of an angstrom. This is much, much bigger, 100 times bigger than this intermolecular distance. And so we take all of these in an element, take the average properties of this, and start talking about all the laws and everything else that we have learned in this course. So whether it is talking of specific volume, specific U, H, S, or any G and A and all those properties, including pressure and temperature, we are assuming that it is a minimum size of an element is this much, and only because of that we are able to assign properties to that. We cannot assign individual properties to each and every molecule and hope to track every one of them in a problem. So that's the difference between statistical and continuum mechanics. Some aspects of this can come from knowledge of statistical mechanics, but not the opposite. So that's the difference between classical thermodynamics and statistical thermodynamics. If you want to look at things like reactions and mixtures in a very, very fundamental sense, one has to go to statistical thermodynamics, and that's not the subject of undergraduate thermodynamics courses. We do that typically at postgraduate level and at research levels. So there you have to learn statistical thermodynamics.
Good morning, sir.
Good morning. Yeah.
Question is, what is the difference between mechanical and thermodynamic work?
Mechanical and
Thermodynamic work, and which devices are used for, means in which devices mechanical work takes place and thermodynamic work takes place?
okay, so simply, if we look at what we have learned in this course, right in the beginning, we defined what was thermodynamic work. That when a force causes a displacement of a system boundary, this we said is work. And we said this is thermodynamic definition of work. Now this includes everything. It includes a mass being pushed and taken through a distance, or a shaft turning around and giving a torque at a certain speed and doing work on something. So this could, all of that would be then classified as what you have called as mechanical work. But this includes electrical work. That means current flowing through a device, a conductor or a heater. When the current flows through it, there is work inflow into that system. So current is because we have a charge going across a field. We could have magnetic work, a magnetic dipole going in a field, or we could even have like the cylinder piston arrangement. There's gas pushing against the piston and doing work. Yes, push, that we would call it mechanical work. Or say the pulling of a wire, or increasing the surface area of a device, say surface tension working to produce work. So strictly, if you look at mechanical work, we have called F dot ds primarily as force on a rigid body causing a displacement. That you may say that is mechanical work. But thermodynamic definition of work includes everything that includes F dot ds. So charge moving in electric field in a fuel cell or in a battery is still work, but we do not call it mechanical work. So this is a much broader, over-encompassing definition of all types of things where F dot ds takes place. Mechanical work we look at largely only as a rigid body being acted upon and a displacement taking place. Okay, so that is the difference. So mechanical work is a subset of thermodynamic work.
Good morning, sir.
Yeah.
I'm Gokul from PhD Tech, and I have the
Yeah.
doubt that in a refrigerant R134A, what does 134 signifies?
Okay. The question is, in many problems I have put down refrigerant is R134A. What is the meaning of 134A? So very quickly to tell you a history of these things, it started off with various refrigerants like R12, which is now banned. This is CCl2F2. Then you got R22, there is something else. So there's a formula by which we convert this molecular structure into this part. So from there, you can look up web or literature anywhere and you can figure out what is the molecular structure of R134A or R410A or things like that. Okay, 410 and 5 series like R500 or R502, these are slightly different from these because all of these are pure substances, whereas these are mixtures for which we have chosen two different molecules, mixed them in a certain way that their property is sort of a pure substance. So that's what it is. I don't, in the notes I put down there, this I don't remember the exact formula of this, CCl, CF2 or something like that. But there's a very small method by which you develop these numbers. You can look up on the web or a book. I don't remember it exactly.
Thank you, sir.
Morning.
Yeah.
Arun Thakra. My question is, what is the criteria to select any refrigerant or coolant for a
Okay, so the question is, what is the criteria?
what is the criteria to select a coolant or refrigerant for a system?
Okay. Okay, I'll slightly broad-base this question. It's a very important and a fundamental question. So what is the criteria for selecting any working substance? For a cycle or a system or a process. So what happens is, let's take the case of refrigerants. In the case of power plants, almost always we use only water. And a reason for using water is, firstly, it is abundantly available. Second, its properties are such that they are reasonably good for doing the engineering of it. And the trouble is, if I can use water in a power plant, why can't I use water in an air conditioner? And this is a issue that will show you why majority of the air conditioners that you see do not have water as the working substance in an air conditioner. There are some air conditioners where water is the working substance. And if you want to see the exact numbers that are coming out of this, I suggest you look up the module 3 assignment. I think it's the last or the second last question, I don't remember which one, where I've posed exactly the same question, that I want a certain heat transfer rate, and I have a refrigerant which is say R134A, or refrigerant like R22, or refrigerant like water. Now, problem with water as a refrigerant is that you cannot go below 0 degrees Celsius. So you cannot use it in a refrigerator to get minus 10 degrees Celsius and keep ice cream. Whereas all the other materials are good, so they can do the job. So water for a freezer, not possible. For air conditioning, when you want temperatures like 10, 12, 15, 16 degrees Celsius, water can be used, it is used. The trouble is that there are many criteria which go in deciding how do you select these things. Besides, the first comes, of course, the thermodynamic criteria. So if you look at the thermodynamics of these and say, well, what is the cycle in which I will operate? And you say that here is my TS diagram, and I am going to operate it between these two temperatures. So for some substance, this could be the saturation dome. For some substance, this could be the saturation dome. Some substance, this could be the saturation dome. So what happens is that in this case, you will never get a condensation if I have used this with this condition. These two conditions, this and this, are both okay. So in this case, what will happen is that the cycle will become like that. Your condensation will be there, and then the throttling will happen over there to this temperature, then there, and then it goes over there. In this case, it will be something like that, but here it will come over there, like this, and like that. Sorry, here. Now what is happening is, you look at these two states, and you say, first of all, my cooling rate will be m dot into the change in the specific enthalpy. Say H1 minus H2 or whatever that may be. Now, do I get a sufficiently large delta H from this state to this state? And if you see that problem in the assignment, you'll find that for some refrigerants, this value is a few hundreds. For water, this value is a couple of thousand. So you say, good, great. For water, this is very big. So I need a very small flow rate. Water is a nice refrigerant. But you look at the other properties now. So you ask that this is my first part. How big will be my equipment? And say, well, what is the specific volume at these two states? This is 1, this is 2. And you go back and pull out V1 and V2. And you will see that for water at 6 degrees Celsius or 5 degrees Celsius dry saturated vapor here, V2 is huge. That means the specific volume has become so big that I need a very, very big pipe to make this thing flow. And that becomes impractical. Unless we are able to control it and redesign the machine to take care of that, then we can do it. So we say, well, water is not very good. Then coming to all the other substances which are possible, we said that we were all these CCl2, F2, CCl, HF2, all these type of families are there. But why did they come about? Because the properties of C3, H8, C4, H10, these are also very suitable as refrigerants. And initially when ozone layer depletion came as a problem, you had to replace R12, and some of the things that were talked of was propane, butane, or mixtures of propane and butane. This is, well, the first criteria would be that, is it safe? Safe for the machine, that means you should not react with the machine or the oil, and safe for humans. What if it leaks out? And the nice thing about all these halons was that they were non-toxic. They did not react with the oil, they did not react with the components, the materials from which you made the component, aluminium, brass, or copper, or all those things. And so they became very, very popular. And they had very nice thermodynamic properties. The specific volume increase was also not very large. So they were great chemicals of the Industrial Revolution. But in 20 years, we saw that they were causing ozone layer depletion, and now we had to throw them out. So we started looking at different things which have less of chlorine, maybe less of fluorine, and start coming to other substances. But then these would also be okay. So, but then these are not very safe. They are combustible. If they leak out, you could have a possibility of an explosion. Inside the system, where there is only this substance, there is no way that there will be an explosion. Specific volume is one consideration. Then you look at the pressures that you get, the pressure here and the pressure here. For water, if I would 5 kPa there and say 80 kPa over 80 degrees C here and 5 degrees C here, the pressure here is very, very small. So this pressure, P1, P2, they are very much less than ambient pressure. But this is of the order of, I think, 3 kPa at 5 degrees Celsius. Ambient pressure is 100 kPa. What it means is that your entire piping and all the joints that you make, connections that you make with the pipes, they have to be very, very good. Otherwise, air will leak into the system. The moment air leaks into the system, the performance deteriorates very rapidly, and you have a big problem. So you like that the pressure should be just above atmosphere, so that air doesn't get into the device. So that's another criteria, that the pressure at this should be not just about atmospheric pressure, and this should not be very, very high. Not 60, 80, 100 bar, maybe 20 bar, 50 bar, 30 bar, something like that. So that's the second criteria. Specific volume was another criteria. Then we look at heat transfer rate, safety, and then, of course, as an engineer, you always have to worry about cost and availability. And these days, like it started off this whole thing, environmental impact. So these are many issues that decide which substance to use in the refrigerant cycle. But the starting point is that you say, well, does the thermodynamics make sense? The thermodynamics makes sense and the engineering is doable, then that becomes the candidate material for the next step of consideration. Okay. If the thermodynamics doesn't make sense, then we are in trouble. Might as well forget that material and go to something else. So before I leave this, let me tell you that water is used as a working substance in a refrigeration machine called a vapor absorption refrigeration system or vapor absorption machine, VAM. We cannot make very small window AC type of things with VAM, but large things like 60 tons refrigeration or bigger 300 type, they are very much there. And if you have waste heat source, they are very, very good options because the electric power consumption is 1/10 or 1/20th the power consumption of a vapor compression system. So energy efficiency wise, carbon footprint wise, these are great stuff. but the engineering is not at all easy in this case. We do not use conventional cycles. We take water and then we dissolve it in a salt, and then we pump the salt, so the work produced for required for pumping is very small, and then we heat it to get the high pressure vapor back, condense it and use it for the refrigerant. So do keep in mind, look up the website and see vapor absorption machines. There are 3-4 Indian companies that make it. They are used in many places and they are a very attractive option because they are very, very energy efficient. Okay, so we'll conclude here, and we have some more devices to look at. We will do them tomorrow. I'll solve a few problems, then we will go and we'll spend some time looking at vapor power cycles, the engine cycles, and see how to do the analysis of that. So with that, we stop here.